Hello, Augies Worldwide. I'm Dave Kassler, amateur radio call sign KE0OG, here with another episode of Ask Dave. In a recent video, fellow YouTuber Kevin Laughlin reviewed a Geiger counter, and I was so intrigued I just had to have one. It's less than $100. Very interesting. It is the GQ Electronics GQ Geiger counter GMC-320 Plus, and I will put a link on Amazon where you can get this. It's in a nice little box. It hints on the website that this is made in America, but it just lives and breathes Chinese, so I'm not going to make a claim that it is. It comes with a little manual. Here's the actual Geiger counter, and it has a little card that I attached that has the limits for radiation. And it comes with a USB cable, and this is just a bag. There is software on the website. Kevin reviewed that software a little bit. I'm not going to do that today because I'm going to take a little bit different approach so that I'm not just repeating Kevin's video. I want to talk a little bit about radiation and what you can do with this thing. The thing is very simple to start up. You just push and hold that button. The battery, well, you got to hold it long enough for the thing to go through. There we go. There's a battery inside, and you can get it out. It's the size of a AA, but it is rechargeable, so you should charge it through the USB cord. It's becoming a lot more common these days for devices to be charged through USB, and this is an example of that. Now, it comes up counting in counts per minute, which is, you hear the little click there. And it does counts per minute. You can also do it in microsieverts per hour and millirads per, or millirem per hour. Okay. And then it goes back to counts per minute. There's a lot of stuff that you can do in terms of the user display. You can turn the little speaker on and off. I know that clicking sound drives my wife crazy, but the light will stay on so that you can see it. You can also save the data that you're collecting, so it can go into a computer, and all kinds of things that you can do like that. And you can set it for doing it just around a certain time or whatever. This is used for going back and forth between menu options. The easiest and most straightforward one is the number of counts per minute. Now, there is a little card here that comes with it that gives you, well, it tries to look as though it's authentic. Counts per minute, microsieverts per hour, and millirems per hour are not synonymous. They don't mean the same thing. It's not just different units in a different system. I did a little research on that and about radiation to see what I could come up with. This, by the way, is about background radiation where we are. We're up at 7,000 feet. So in the house here, it's 23 counts per minute. I did a count in a couple other places. Here, I asked my wife if she had any antique glass that was green. And here is a piece of that. It's a little nut bowl. And if you put this into it, you'll find out that the number of counts per minute goes up quite a bit. This old glass indeed was colored using uranium dioxide, which back in the 20s and 30s nobody thought anything about. Now note that the background radiation that's coming up there is not that high. It's about double normal background radiation at this elevation. Should you use this dish to eat off? Yeah, why not? I mean, we're talking background levels of radiation. Let me just turn that off for a second by pressing and holding. And I want to go through some charts a little bit about radiation, just to give you a little bit of a feel for what we're talking about. Now, I've made the point many times that ham radio radiation, HF, VHF, UHF, microwave, is non-ionizing. Non-ionizing means it doesn't knock electrons off of atoms or things like that. However, the radiation that we're talking about here does. It is ionizing radiation. Now, this book, I've just printed the first page here. This is available at DTIC, the Defense Technical Information Service or Center, and you can download this for free. This is the Bible on radiation. It was put together many years ago. This is a subsequent, it's the third edition, published in 1977, The Effects of Nuclear Weapons by Glasstone. Okay, all you have to search for is Glasstone, Glasstone, and Effects of Nuclear Weapons, and you'll find this on the DTIC website. You can print it as a PDF or download it. You can buy copies of this book, but copies are a little hard to find and are remarkably expensive, $60, $70. I don't think it's worth it because, other than owning a piece of history, this is unclassified. It's put out by the Department of Defense and the Department of Energy. A little known fact in the United States is that atomic energy, including nuclear weapons, is the province of the United States Department of Energy. In fact, they were formed originally to pull the nuclear weapons business away from the Department of Defense. So they're all managed there. So there's a part of the DOE that doesn't deal with solar panels and wind turbines, but deals with nuclear weapons. And of course, they license and regulate and supervise nuclear power in the United States. Now, I want to tell you a little something about this book. It is the Bible for effects of nuclear radiation. There's a whole chapter in this book on EMP. If you've heard about EMP, electromagnetic pulse, and you're afraid of it or something like that, read the source. Read this. This is the sum total of information that's been made public is in this book. But we're not worried about EMP today. Let's talk a little bit about radiation and the kinds of things that can cause a Geiger counter to go off. There are three main kinds of radiation from nuclear events, and a nuclear event, by the way, includes uranium buried under the ground, radioactive sources, and so on. Nuclear fission produces three major particles, plus some other things here. Alpha radiation, which is a helium-4 nucleus, 2 protons, 2 neutrons together. It's just the nucleus of the helium atom. And that's alpha radiation. It's actually particles, pieces of atoms. And in the process of fissile material going radioactive, the uranium breaks apart and releases, in addition to things like strontium and iodine and so on, releases alpha, beta, and gamma radiation. The alpha radiation can be stopped by something as thin as a piece of paper. That's right, your t-shirt can stop alpha radiation. Now, because of the way the Geiger counter is constructed, there's a glass tube in here that's the actual Geiger-Muller tube, and alpha radiation is not going to make it through there. So although technically the process used in the Geiger counter for counting radiation could detect alpha radiation, it can't make it past the glass and the plastic. So we're not going to worry about that. Beta radiation are free electrons. Now, electrons, these are very high energy electrons, very high energy electrons. They'll go through the paper, but they would be stopped by a conductive surface like aluminum. Okay, that would stop it right there. Now, the gamma radiation is actually electromagnetic radiation. Okay, it's electromagnetic. So, in particle terms, we'll say it's a photon with extremely high energy. And it's very difficult to stop the gamma radiation from going out. Lead-lined walls, thick concrete walls, lots of dirt, things like that can greatly reduce the gamma radiation. So the Geiger counter will definitely detect the gamma radiation and probably the beta, because this thing's made of plastic and glass to get to the Geiger counter too. Now, there's other kinds of radiation. Neutrons come from nuclear reactors. Remember, the way fission works is neutrons hit atoms, split them apart, yada, yada, yada. So there's a lot of free neutrons flowing around. Neutrons can be stopped relatively easily, but here's the thing. A neutron is the only kind of radiation, that can cause something to become radioactive. So in every major hospital in the United States, buried deep in the basement, very difficult to get to, is a small atomic reactor. There's not enough nuclear material in there to go critical and create lots of heat and all this kind of stuff like that. But it is a small amount of fissile material, meaning uranium, plutonium, designed specifically to create a lot of neutrons. And then they put dyes down in next to the nuclear material, and it makes that dye radioactive. And then what they do with that is, like, before I had my prostate surgery, they injected me with some of this radioactive stuff and then used basically a very fancy picturing Geiger counter to see where the radiation accumulated, because that particular dye tends to accumulate in the body where the body's most under stress. And so it fortunately showed that the cancer was limited to the prostate, so they got it all out. But neutrons will be counted here too. X-rays is ionizing radiation, like dental X-rays, things like that. And then there are the cosmic rays, which are extremely high energy photons, again, that come from outer space. They're extremely high energy, the most high energy photons, which means they have the highest frequency of any of those effects. Now I want to talk a little bit about dose rate versus total dose. Think of it this way. A dose rate is the rate at which something accumulates. It can be measured in millirems per hour. That's Rankine equivalent man. Millirems per hour, that's a rate. It's like being paid $15 an hour, okay? It's a rate at which you're paid. The total dose is measured in Rankine equivalent man, and it would be like total money. Like, for example, you inherit $5,000. You get it all at once, okay? Now, in radiation, getting something all at once is a lot worse than getting it spread out over a period of time. Let's also look at, because I'm going to show some charts from the Department of Energy, in hours versus years. 1 year is 8,760 hours. So 1 millirem per hour is the same as 8.76 rems per hour, or per year, 8.76 rems per year, which, by the way, is a lot of radiation. So let's look at a couple charts here. This is a radiation dose chart. You start out with the blue, okay? And in the blue, living within 5 miles of a nuclear power plant for a year will give you 0.09 microsieverts of radiation. Now, if you take all the radiation from these sources, it ends up being one green block. And then the green blocks are getting bigger things. For example, the chest CAT scan will give you that much radiation. And 3 of those little dots are the same as this entire thing here. And notice we're going not linear but exponentially here to where we get into doses that can prove lethal. Doses can accumulate and be lethal, or they can go up very suddenly and be lethal. Now this is back in REMs. Here's there's Sieverts, there's Grays, there's REMs, there's Rankins, there's all kinds of different ways of measuring this stuff. It can be very confusing. This chart builds up from the bottom. You can download this chart. I'll put the link to it from the Department of Energy website. There is a version of it on Wikipedia, but it's not as high res as this one here. So we look down here. This is millirems in total radiation dose. Okay, so it doesn't have much to do with the rate. However, they mix and match on this chart. It's kind of weird what they do here. Okay, so down here at millirems per hour, at less than about 2 here, is the EPA dose limit for public drinking water of 4 millirems per year. Well, is water radioactive? Well, yeah, there's stuff down in the earth that will do that. NRC nuclear cleanup criteria for site commissioning puts it right in here at 25 millirems per year. It's not very much radiation. Now you take this whole thing and we're going to multiply by 10. The natural background radiation that you're going to get in the United States is 310 millirems per year. Now, I live at a higher elevation. Here's a place in China where they have high natural background radiation. And in fact, we can look over in here to India and Brazil and even a place in Iraq where they have very high levels of background radiation. You can see where Iraq gets its nuclear material. They have their own, okay? They have their own. Now you start getting up here, see, okay, regulations and guidelines down here. Medical diagnostics are in this area. Like a K is an abdominal CAT scan, CT scan, okay? Will give you that much radiation in the few seconds, actually, that it takes to do it. H is a PET scan of the bladder. There's all different things they do there. Now, when you get up into the REMs, 0 to 100 REMs, you start getting into areas where there might be problems. For example, if you get up into the 40 or 50 REM area, if you have acute exposure, meaning sudden exposure to that much, you might be talking about some radiation poisoning at this point. Now, note, here's a problem. Interplanetary space. These people will get somewhere between 40 to 70 REMs of exposure in traveling to Mars or something like that. That, by the way, is an unsolved problem. Remember I mentioned it's very hard to shield against gamma rays? Well, it's very hard to shield against gamma rays. So they have a similar problem getting up to the space station and so on. Now, when you get up into this region right here, 100 to 1,000 REM, we're talking about serious radiation poisoning. And the death starts to happen in here. If it's over 1,000 REMs for whole body radiation, you're looking at death. Okay, it will kill you. Now notice we keep going up by a factor of 10 to 10 to 10 to 10 to 10. Okay, the amount of radiation that will kill you is many. Let's see, 1 factor of 10, 2 factors of 10, 3 factors of 10, 4 factors of 10. 5 factors of 10, 100,000 times more than you're getting from something like my wife's little green bowl. Okay, so that gives you a little bit of background. Let me show you some things that I measured. This photograph shows the background radiation here. This particular picture shows I went down into the basement in the lowest spot in the inhabited part of the house and put this in there and tried to do it in a way that I didn't disturb the air very much, because I wanted to see if there's extra radiation from radon. And I found just a little bit, but it was still well within background levels, not an issue. So I took the Geiger counter outside and put it on the ground. Now, we live not far from where there are uranium mines, 50, 60 miles. And so the ground around here is kind of in the same geological time frame as that, and there's a little bit more there. But when I get up here elevated in my room, which is maybe 5 or 6 feet above the ground, there's less radiation at this point. So it's a fascinating subject. If you want to learn more, go to Wikipedia and look up radiation and find out all about it. If you want to know the truth about what nuclear weapons can do, the effects of nuclear weapons is your Bible, okay? Look up Glasstone Effects of Nuclear Weapons, and you can download the whole book. It's 800 some odd pages, but it goes through very carefully and catalogs just about everything we know about the human body and radiation. Also read the chapter in here on EMP. There's a lot of folklore about EMP and not very much truth. This is the guide for what's real out there. This is what utility companies and other people plan for from this, not from some local pressure group who thinks they ought to do more. So there we have it. Please check out, if you would, dcastler.com/support. And, you know, there's a tip jar there. There's a recurring tip jar on PayPal. There's Patreon, which has slightly higher fees for me, not for you. And there's the thumb drives. And I now have an assistant. My assistant's name is Lauren, and she is 2 years into her college, and she'll be around for a while, and is going to help me get the general videos updated. And when we do that, we'll have a general thumb drive also. And thank you very much for your time. It's really my pleasure to come into your home. Thank you so much for having me. And until we meet next time, 73.